effect of an artificial pancreas on the stabilization rates of glucose levels within the human body. So diabetes is an incurable disease that affects 415 million people worldwide and costs the U.S. about $245 million annually, coming to about $7,900 per person. And that's quite an extreme amount of money to be paying for solely medication in order to survive. And so with the rising price of insulin to over 300% in the past decade, many people have had to come to the tough decision of whether they can afford other common necessities such as food and shelter in order to receive the necessary medication that they need to survive. So our experiment tested whether or not an artificial pancreas could be a less costly solution to insulin injections, and an artificial pancreas would regularly regulate the glucose levels within the bloodstream of a diabetic in order to make sure that their glucose levels were stabilized and they weren't at risk for further health issues. The hypothesis for our experiment came to if an artificial pancreas was created to replicate the functions of an artificial pancreas, then alternative treatment methods could be found in order to help suffering diabetics.
So we were often asked how our experiment related to what an artificial pancreas would do in the human body. So we had a basic solution and an acidic solution, and those would represent the insulin and the glucose inside the human body, and then the pump connecting the two would be the pancreas.
Materials that we used included a 75-watt power supply, an indicator solution called bromethymol blue, which indicated the pH levels of the different solutions, and a peristaltic liquid pump, which took our acidic solution and put it into our basic solution to neutralize it.
In order to make our conductivity sensor, we took a piece of styrofoam and attached it to copper wires that connected to a straw at the bottom and was placed inside of
neutral solution, and then was later moved into the basic solution.
So to begin the procedure, we had to create our solutions, and we took 14.3 grams of baking soda and put it into 200 milliliters of distilled water to create our basic solution. And then we took 200 milliliters of distilled white vinegar to create our acidic solution.
And then for our basic solution, we did the same thing that we used to create the basic solution, but because we had to make it neutral, we had to put another set of the basic solution in with another 100 milliliters of the distilled white vinegar. And we found that although the experiment had originally said that we needed a 1-to-1 ratio for the neutralized solution, that we had to do a 2-to-1 ratio with more of a basic solution than an acidic solution.
In addition to that, the basic solution that we added to the neutralized bowl, half of it came from the original basic solution, but the vinegar remained at 200 milliliters.
The second part of our procedure was to take our peristaltic pump and attach tubes to it, one tube attaching to our acidic solution and one tube attaching to our basic solution. And the first step, we had to prime the peristaltic pump.
So what we did is we put both tubes into the vinegar solution and ran the pump just to make sure it had like all the little bugs worked out and everything, so it worked properly. And then after it was properly primed, we moved one of the tubes from the acidic solution into the basic one and began to run the pump again. The pump then took the solution from the acidic bowl into the basic bowl, which the conductivity sensor was already in, and then it would effectively neutralize the solution by pumping the acidic into the basic.
So the next part of our experiment was to really see whether a reaction had taken place, and so we could see that after 30 seconds of the pumping in the acidic solution into the basic solution, that a reaction had taken place, not only by the indicator that had turned green, but also because a sort of bubbling effect had taken place, so that you could see that a chemical reaction had also taken place, and also the conductivity sensor began to smoke, which kind of indicated to us visually that a reaction had taken place.
So in our experiment, it was very complex, and unfortunately there were a couple of errors. One was that our breadboard was not the correct breadboard that was suggested in the original procedure. And along with the breadboard, we were supposed to be having resistors. Unfortunately, those resistors were also not the correct ones. So we had to go towards a different power supply. And also we were supposed to be using 8 AA batteries, but they were not strong enough to power our peristaltic pump, which is why we used the 75-watt battery supply.
Yes, so the change between batteries was we had to originally use 8 AA batteries, but because that wasn't strong enough to actually function the pump by itself, we had to convert that to 12 volts, which we got in the 75-watt AC DC power supply.
In addition to that, the lack of resistors made it so that the pump would steam when neutralized instead of completely turn off.
So after we conducted our experiment and our research, we concluded that an artificial pancreas would be a more cost-efficient method to insulin injections, and because it would only cost about 14 months of insulin treatment compared to the lifelong amount of treatments and injections that you would need in order to combat irregular glucose levels, an artificial pancreas would be a viable solution, but we only did this experiment for type 1 diabetics solely because type 1 diabetics are the ones that need insulin injections, whereas other forms of diabetes don't need the regular insulin injection treatment method.
Okay, so in the future, advancements that can be made to our experiment include taking the opinions of people who do suffer from diabetes and whether or not an artificial pancreas would be a viable option for them and other people suffering. In addition to that, we could identify the risks that come along with an invasive surgery to put the pump inside of the human body. Comparing how long it takes to regulate with the pump versus another form that they're already using is really crucial, because if the pump can't regulate in time because of some malfunction, then the person will be sent into ketoacidosis and it will threaten their life.
In the top left picture, you can see our setup. In the middle displays our power supply. Then the bowls, the blue one represents basic, the green represents neutralized, and yellow represents acidic. And then here's another example of how the basic solution is turned green when the pump pumps in the acidic. All photographs were taken by the researchers.